attending our short course on the decision intelligence for two-sided marketplaces. I'm one of the instructors for this short course. And this is the agenda for our short course. I will cover the first part, and then Tony cover the second and third part, fourth part, and then Chen Chen also cover the third part. And I'm going to introduce the foundations of the two-sided marketplaces. And in over the last decade, we have seen many developments in AI tools. And many AI tools were originally developed for the business or for the government. But its real impact emerged when it reached the customers. Okay. And in last decades, we have seen many AI tools having widely used in society, economy, business, and manufacturing. And in the last, since 2018, Dr. Michael Jordan has consistently mentioned about the 4 phases of the machine learning successes. The first phase is the backend, started from the 1990s to 2000, is mainly developed the tools for search for the fraud detections in the various e-commerce. The second phase is on the human side. It started from 2000 to 2010. It mainly developed various basic machine learning tools for recommendation systems and have the wider applications in social media. The third phase is ended from end to end. It started from the 2010 to now, and it has empowered and speech recognition, computer vision, and translation. The further phase is on the markets. Okay, it's in emerging areas, since the 2018, and it's mainly talking about integrate AI tools with our real life, the human real life. And what is the two-sided marketplaces? And a two-sided marketplace is a market where the one or more platforms facilitating interactions between the two or more distinct user groups. The platform goal is to bring both sides on board by properly structure incentives such as pricing, accessibility. There are 3 major key characteristics. The first one is interdependency. The value of the one side depends on the presence and the engagement of the other side. The second one is a platform as an intermediary. The marketplace acts as a bridge, reducing transaction costs and enhancing trust. The third one is the pricing strategies. The platform uses pricing and the subsidies to attract and balance supply and demand. Here are some concrete examples of two-sided marketplaces. And I think that everyone are using these days. They are basically, here I list the Airbnb, eBay, Amazon, and the Didi and the Uber. There's both for all these marketplaces, they have side 1, side 2, and platform providers. And I use the ride sharing as a complex as an example. We know that the ride sharing is a complex spatial temporal systems. And also there's the relationship between there are 2 sides. One side is the riders, the other side is the drivers. The relationship among the various variables are nonlinear, and also the supply and the demand, and their relationship are interactive. And also there are the various basically environmental factors and also influence the system. And therefore the causing these kinds of uncertainties in the system. And also there's a kind of the causal relationship among the various kinds of policies and also the supply and the demands. And we are basically trying to do since 2018 is to try to develop digital twins for marketplaces. What is the digital twins for marketplaces? It is actually visually replicas of the 2,000 marketplaces that simulate and analyze the real world interactions between the buyers and the sellers, or supply or demand. Those AI-driven models integrate real-time data, historical trends, and behavior and analytics to optimize the decision making, improve the market efficiency, and test the policy in a risk-free environment. There are 5 key modules. We are going to mainly cover the first 4. The first one is the supply-demand diagnosis. The second one is the supply-demand prediction. The third one is basically the policy optimization. And the first one is the policy evaluation. Last one is the lifetime values. Okay. And why this matters? Because this is essentially for data-driven decision making and improve the efficiencies and user experiences, risk-free policy experimentation, and the long-term marketplace sustainability. And this is basically the past diagrams basically for digital twins. We list all these kinds of 5 modules on the outside of the circles. And internally, we use our various basically machine learning or statistical tools. Basically, there are 4 major ones. The first one is experiment design. The second one is spatial time and temporal modeling. The third one is the graphical modeling. The first one is deep reinforcement learning. And internally, basically, we use causal inference, statistical operation research, and machine learning. Our eventual goal is to develop the marketplace Alpha 0 for the systems. And what is actually we try to develop here is the spatial temporal causal digital twins. And these are some of the key components or key variables people care about in this area. The first one is the microscopic business indicators. Right? This overall supply-demand balance is influenced by external factors and the platform, the policies. Okay, because there's many for the different basically marketplaces, the different business units they have the different business goals or metrics. The second one is the supply to demand matching degree. This is try to measure how the effectively supply meets the demand at a given time. The third one is the supply side. Is availability of the providers responding to the demand fluctuation. The first one is the demand side, the volume of the user request at a different different times and locations. And also we have the different platform, the policies, like the first one, like dispatch and the scheduling. The second type basically is the pricing and the subsidies, okay? And besides all these variables, all the metrics, we're also interested, there's some external confounding variables, like weather, holidays, work days, infrastructure, and government policies. Okay. We wanted to understand how does all these key factors or key components are related to each other across time and across locations. We are focused on the 4 mathematical kinds of the formulations. The first one is the future macro indicators depends on supply, demands, and matching. That's the most important basically business analytics modeling we want to do. Second one is the matching degree is influenced by the real-time supply, demand, dispatching policy, and environmental factors. The third modeling we want to do is the supply levels depends on the past demand, the matching efficiency and pricing, and the subsidies. The last one is the demand levels are affected by past matching, pricing, subsidies, and environmental conditions. That's basically the 4 major modeling strategies we try to do. And the first one I started with basically supply demand diagnosis. Okay, this is basically the first most important kind of modules you need to develop for the system. And what is basically supply-demand diagnosis? Supply-demand diagnosis is the process of analyzing and identifying mismatching between supply and demand in a given system. It aims to uncover inefficiencies, imbalances, and factors affecting the equilibrium between what is available supply and what is needed demand. Okay, there are the 5 key steps basically for this supply-demand diagnosis. The first one, basically, you need to connect the data and do some simple, relatively straightforward the business analytics. Basically, you're gathering historical and real-time data on supply and demand trends. The second one is hotspot detections. Okay, you need to identify shortages or surpluses across time and across locations. And also you need to do causal analysis. You need to integrate underlying factors such as pricing, the external market conditions, policies, and all the operation constraints to find what's the cause of the supply and the hot spots. The first one is the impact assessment. We need to evaluate how these imbalances affect the business performance and the customer satisfaction and operation efficiencies. The last one, we need to take these corrective strategies. Okay. Then we need to recommend basic policies, pricing adjustments, or operational changes to restore the balance. Okay. These are basically the 5 key steps of this supply demand diagnosis when you try to set up kinds of the system. Why this is important? The first one, why is important? Because first one is can prevent inefficiencies. Okay. The second one is to improve the decision making. The third one is to enhance market stabilities. And you can reduce volatility by ensuring the better alignment between supply and demand. The last one is to boost the profitabilities. They help optimize cost and maximize revenues by addressing imbalance effectively. Okay, and this is quite very important. And for these kinds of the companies, there's a wider range of application of supply-demand diagnosis in these two-sided marketplaces. I give some of the examples. One is basically ride-sharing platforms. Okay, and it happens basically almost every day. And the second one is basically retailers and e-commerce. The third one is basically healthcare systems. Basically, for instance, you need to assess the hospital bed availability against the patient needs to optimize the resource allocation. And the last one is the energy marketplaces. Okay, and the balance electricity productions with consumptions to prevent blackouts and efficiencies. Okay, this is why this supply demands is so important in practice in our real life. Okay, we basically mentioned about some of the key steps. Okay, and then the following sections we're going to discuss specifically how to handle these cases. And the first one, basically, for most of these two-sided marketplaces, we need to develop basically this graph-based equilibrium metric. Why the key motivation is basically we need a metric to measure the supply demand and equilibrium. The object, we needed to come up with an object function for improving strategies of dispatching, pricing, and incentive optimizations. Because we need some of the concrete metric. Okay, so easily computable and basically very interpretable and can easily to do downstream analysis and identify strategies. Okay. And this is the graph-based equilibrium metric, a set of measures used to evaluate and quantify the balance between the supply and demand in a complex systems. Okay, and basically it can be represented as a graphs or networks. Okay, these metrics help us to assess how well the supply nodes and are matched with the demand nodes, and well considering connections, constraints, and the network effects. These are the key steps, basically, for the graph-based equilibrium metric. And the first one you need to do is the graph representation. Basically, you need to represent your system as the bipartite graphs and all general graph. This depends on the type of applications or the type of companies you're working. And you already know that it represents the supply and demand entities at certain levels, whereas the ages represents the potential interactions assignments. This really depends on the concrete, basically, scenarios. Okay, and different marketplaces may have the slightly different the graph representations. The second one is the matching efficiencies. Okay, we need to measure how the effectively supplied nodes are connected with the demand nodes. And some of the concrete kinds of metric, like the maximum of matching rates and the average of the matching distance and other things. The third one is the fluid equilibrium. And basically, we need to examine the distribution of supplies relative to the demands over the networks. And some of this concrete basic metric, like Vasasa distance, to measure the distance between two the distribution. The first one is the hotspot identifications. We need to identify the overloaded basic nodes or edges where the demands exceeds the capacity. The last one is the dynamic adjustment of policy evaluation. We need to assess how small the interventions and the shift to equilibrium status, like complete like sensitivity analysis equilibrium shifted with the small perturbations. Okay, we need this kind of basically for the graph-based equilibrium metric. We need these 5 key steps for all these kinds of construction. I just use the ride sharing as examples. This is how do we basically construct this graph, right? The nodes and the relationship. And this is basically the left one is the dynamic supply map in a city in China. And we divide this the whole cities into this kinds of hexagons, and also this kinds of we count the number of the basically supplies in each of this shape. Okay, easy same. The right side is the demand maps. Basically, they also have the frequency in a given period, like 5 minutes, every 5 minutes in each cell. Okay, and actually you can basically use this one to define the nodes and also define the relationship. And the second things you need to define what is the matching efficiencies. And for here, I just use some simple examples. There's the passengers and also the cars. Okay. And here, basically, we after we define the graphs, and we can characterize the age informations like the weighted matrices, and also because for these kinds of applications, actually the drivers can move around. Okay, and the passengers usually stay the locations. Okay, and actually we define this transport cost on the graph from the one location to another node. Okay. And the last one is basically we need to measure the two kinds of metric and between these two graphs. Okay. And the third thing is to try to calculate the flow equilibrium. In our framework for the ride sharing, basically we consist of 3 steps. The first one, you have initial distribution of the supply and the demands. Okay. And the second thing is because the drivers can move around. Okay. And this is basically the second one is called optimal transport because the drivers need to pick up the passengers. Okay. Usually the drivers may be 1 mile or 2 miles away from the passengers. Okay. And basically that's the involved kinds of the optimal transport. Okay. And the third one is after transport. Basically, you match this each of the pair of the passengers and the drivers. Okay, after the transport. And actually, in practice, if you choose the size, and if you vary the size of each of these cells, and actually we can get a multi-level representation of the optimal transport functions. Okay. And this is the basic mathematical definition of the graph-based equilibrium metric. And this two metric is basically measure the distance between the supply and the demands. Okay. And the supply, basically the demands minus basically the transport supplies. Okay. Plus the cost of the transporting the cars to pick up the passengers. Okay. And actually these problems can be solved as the unbalanced optimal transport problems. Okay. You can use the linear programming to solve it. Okay. And also we can take the slightly different the views. One we can take this demand-centric views, and another one is supply-centric views. Okay, if we have to take different views, then this can be used in different scenarios. Okay, and actually just now we described how to calculate the equilibrium metric at each time frame. Okay. Because in practice, you have to calculate this kind of equilibrium metric almost every 10 minutes, or it depends on the scenarios. Okay. And in practice, when the given time, the t minus 1, you have the demands and also you have the supply. You can calculate the supply, the demands, and the matching at the t minus 1. Okay. Based on these kinds of the supply demands matching, and this kind of, you can regard it as the micro index or micro metric. And then you decided what kinds of policy you're going to introduce. Okay, this is the theta t. After you apply these kinds of policy, and you're going to, and also you're going to get this new demand at the time t, and the new supply at the time t. And then you can calculate the supply and the demand metric again, and you get a macro the index, and then you decide whether you are going to, take advantage. And you are going to apply another set of policies, theta t minus plus 1. And after that, basically, you can get these kinds of spatial tempo, these kinds of the demands and the supply maps, and the supply and demands matching metrics, and also you get these kinds of policy across time. Okay. After you get all these kinds of information, so the next thing is you basically, as a manager, you need to do is do dynamic adjustment and the policy evaluations. Okay. The first one, basically, for dynamic adjustment, you need to do these kinds of real-time incentive adjustments. The second one, you need to reallocate resources. Sometimes, in particular, in the early mornings, basically, the manager, when they basically run these kinds of like Uber, they are going to adjust these resources, in the early morning. And also, you need basically to identify these kinds of hotspots and mitigate basically these hotspots. Okay. Another thing is basically after you have this equilibrium metric, you can do another thing is policy evaluations. Okay. You can use this equilibrium metric as the kinds of the reward or as a concrete metric to do these kinds of impact analysis of pricing policies. You can do the fairness and accessibility assessment. You also can do longitudinal performance tracking for the whole systems or the whole platforms. Okay. I just showed you some of these concrete examples. How we use these kinds of equilibrium metric to evaluate the kinds of two different kind of dispatching policies in our platforms. And finally, basically, I want to summarize the 5 key components of the supply demand diagnosis systems. The first one is to do this supply demand estimation, okay, across time and across locations. The second one is the predictive models for supply demand forecasting. Okay. The third one is the spatial tempo value calculations. We can use the graph-based equilibrium metric analysis to do it. We also can use reinforcement learning to do it. Okay, we're going to discuss later. The first one is to do clustering and also demand hotspot identifications. We need to identify hotspots. Okay, and then we need to identify, come up with strategies to solve the problems. Okay. The last one is the intelligent incentives and the pricing mechanisms. Basically, when you link all these existing policy in the platforms with all these kinds of the hotspots together. Okay, this is basically 5 key components of SDD system. I'm going to move to the second modules, basically supply demands predictions. This is basically one of the kinds of key components in all these kinds of ride sharing platforms and other basically 2000 marketplaces. Okay, I just illustrated basically why this is, first one, why is the supply demand forecasting important? And there are 7 major reasons behind it. The first one is basically we need to do optimize basic resource allocations. Okay, you want to do forecasting. The second one is enhance the customer experiment. This is very important. Okay, and also want to reduce the cost and operation, improve the operational efficiency. The first one is data-driven decision making. And the fifth one is facilitating dynamic pricing and revenue basically optimizations. The sixth one basically is to reduce risk and enhance stabilities. The last one is to support sustainabilities and environmental efficiencies. Okay, this is basically you can think about for all these kinds of the 2000 markets. This is one of the very important modules besides the first one. Okay. And I just use the supply, use the ride sharing as examples. And the problem is basically in ride sharing, we wanted to predict the supply demands distributions. Okay, and there's three major kinds of the components. One is basically we needed to multimodal data fusions, and also there's basically the complexity come from the complex the spatial temporal patterns inside. Okay. The second one is basically we need to do a lot of transfer learnings because there's a heterogeneous space among the different cities. Okay, like you can compare the DC with, Philadelphia and the other cities. And there's the heterogeneity of the features among the different tasks. Okay, that varies across the basically locations and also across the seasons and also across the time. The last one is basically we need to do these kinds of there's various tools we're going to use, basically the causal inference, the model. We try to increase the model interpretability and also impact analysis. The goal is basically, eventually the goal is basically improve the service the quantities. This is basically the 3 levels from driver side. We wanted to reduce the empty drivings. And for the riders, basically we want to improve the intelligence of travel guidance and less the quizzing time. For platforms, there's various kinds of benefits to the platform. They're basically the key challenges in supply demand forecasting. Okay, it's not like the supply and demand forecasting is highly complex. Due to interplay of the 6 factors. Okay, the major factors. One is basically policy and the platforms driven challenges. Okay, and the second one is infrastructure constraints. Okay, this is quite important for ride sharing, like the transportation and logistic bottlenecks. Okay, that's basically, and the energy resource limitation and the digital infrastructure gaps. Okay, and the third one is basically the environmental and the random event factors. You need to take account of that. Okay, because this creates a lot of fluctuations across the seasons and across time, even in daily. The first one is economic and market dynamics. Okay, like inflations, like current fluctuations, and also changing the customer kinds of behavior and demand efficiencies, and all other things. And the data and the model uncertainty forecasting. The last one is the link supply and the demand, the core challenges basically we need to consider. Okay. And actually, how to build up this supply and demand forecasting. And there's many people are working on this spatial temporal data forecasting problems. Okay, for the 2000 markets, actually we wanted to develop a hierarchical supply and demand forecasting systems. Basically, such a system is a structured, multi-level approach that model the 3 major things. You need to model the macroscopic business indicators or metrics. We are simultaneously predicting the joint distribution, the supply and the demand. Okay. And this system has to integrate the platform policies and the economic factors and the environmental influences and the social trends and the infrastructure constraints to provide adaptive dynamic forecasting in uncertain real world conditions. Okay. We need to do these three different levels. Okay. And here I'm only focus on the last two. The first one we are talking about the micro level, the supply and demand forecasting. I'm just to introduce two papers on this. One of the papers is to we developed a tool called the Spatial Temporal Multi-Graph Convolution Network, the published in AAAI 2019. The second paper is we try to do this kind of accurate origin and destination demand prediction to enhance the ride sharing efficiencies. Okay, that's the second method that we developed here. This is basically the first algorithms, the STMC MGCN. Okay, this is basically the neural network basically consists of three key components. The first one is a graph. Basically, in the graph, we incorporate three major relationships. Okay, and the second one, we do this temporal CGRAN. It's basically we borrow a lot of information from the basically recurrent neural network. We use these context-gated temporal basically modeling strategies. The last one is a spatial MGCN. We take advantage of this non-Euclidean spatial kinds of modeling. These are basically the key components of the detailed information about these two modules, two components of the model. The most important part is the graph generation part. Okay, we consider the spatial closeness, and also we consider this point of interest similarities. The last one is we consider road connectivities, road conditions, okay, transportation constraint. For other two are basically pretty common, and people are familiar with this. Okay, and actually we demonstrated almost 6 years ago. We demonstrated our method is outperform the existing method. And the second algorithm we call the OD, the CECED. Okay, actually, why this is quite a challenge? Actually, in practice, basically, and if you can see the different size of the cells, okay, in practice, and for ride sharing, you will see that. And if you have the high resolution kinds of graph, you will see a lot of zeros, and in many of these kinds of the cells. Okay. And the first issue challenge is the OD matrices grow the expansion with more spatial divisions. The second one is basically data sparsity. So over 90% of the final grade OD flows have zero demands. Okay. The last one is semantic geographic dependencies. Okay. How to address the issues? We develop these kinds of OD, CED kinds of modeling. Incorporate three kinds of the key components. One is the space causing modules. Okay, we merge the fine grained cells into supercells to mitigate in the sparsity. The second one, we take advantage of encoders and decoder architectures. The last one is the permutation invariant OD embeddings. And this is the experiment that basically show that in two cities, our method is needed to over basically 28% even larger improvement, and computationally is our method is much faster. Okay. And also wanted to mention about another basically important strategies, and basically measure the supply demand forecasting. And for this one, we tried to joint predict and supply demand together. We wanted to develop a new framework. Is a causal, interpretable, scalable forecasting framework. Okay, and our method is called collaborative causal spatial temporal fusion transformers. Okay, this is the mathematical basic formulation behind it. And here we try to do causal inference, integrate a lot of information from causal into these kinds of the prediction kinds of forecasting framework. And these are the three major modules. Faster SF, and also CA, the causal attention. The last one is the temporal attentions. Okay, and I want to emphasize this causal attention mechanism is to distinguish our models from the many of existing spatial temporal prediction models. we try to use the causal inference tools, the double machine learning tools, to do that. Okay, and this is the past diagrams and the algorithms for the causal attention algorithms. And this is causal attention algorithms. Basically, the first step we need to consider external covariates. The second one to build a very controlled group and a treatment group, and do double machine learning and get the causal attentions or weights, and using that as a prior information to build into our prediction kinds of framework. Okay, and this is basically illustration. We basically how to use offline data like a rainfall. Basically, before rainfall, we cannot basically do real causal, basically do experiment on the rainfall. But we use offline data to do this kinds of causal inference. Okay, and actually this is the prediction accuracy and improve comparisons with other method. I stop here, and Tony, you can start. I don't do anything. Tony, you need to share.
Yeah, just 1 sec. Let me share the screen and get the system set up.